So we are going to have a look at review on Stoichiometry I. There's a few questions here that will just help us along the way. I'll go through and explain a couple questions at a time. It is recommended that you pause and try questions as we go through. This is more of a correction, and if you really get stuck on a question, having a look at how we should be doing it. So the first question here says, what scientific principle or law is used in the process of balancing chemical equations? So we'll start with looking at that. So this law is called the law of conservation of mass. Law of conservation of mass simply says that mass can be neither created or destroyed during the process of a chemical reaction. For part B, it says, in balancing chemical equations, why should you not change the subscripts in a chemical formula? By changing the subscript, you change the chemical compound. And question C says, how would one write out liquid water, water vapor, and aqueous sodium chloride and solid sodium chloride in chemical equations? So liquid water, we would write H2O, subscript L. Sometimes you can use a written L. Water vapor would be H2O in the gas phase with a little g. Aqueous sodium chloride would be NaCl, AQ. And solid sodium chloride would be NaCl, solid. So question 2 is really just a trial and error type question. It says balance the chemical equations. A lot of times you can get a lot of help just by looking at things, taking a minute just sort of to plan. We have CO2, so we have oxygen kind of locked in 2's here, and we have a 3 here. So 1, 2, 3. So we're just going to put a 2 out in front here, and then a 2 here, and a 1. We'll try that, and if it's not right, we can always go back and change it. So I have 2 carbon, 2 carbon, 2 and 2 is 4 oxygen and 4 oxygen. So that is good. A lot of time we can get a little bit more work done if we actually use a pencil in balancing, whether it's the first time you've balanced something or it's the 100th time you've done it. Let's make this a little bit bigger for us. So you can start with 1's present if you want. I have 5, 6 oxygens. So I'm just going to put a 2 in here, because that will give me 6 oxygens and 2 hydrogens, 2 hydrogens, 2 nitrogens, and 2 nitrogens. I think we're balanced here, so let's just double check. 2 nitrogens, 2 nitrogens, 5 and 1 is 6 oxygen, 2 times 3 is 6, 2 hydrogen, 2 hydrogen. So we get another good balance. We have methane plus chlorine gas giving carbon tetrachloride liquid and hydrogen chloride gas. So I usually look at things that are hopefully the only place we'll see them. So hydrogen is only found in one spot here and on both sides. So I'm going to make this have 4. Now I have 4 chlorine, so I'm going to hit 2. I have 1 carbon, so let's do our check here. 1 carbon, 1 carbon, 4 hydrogens, 4 hydrogens, 4 chlorine, 4 chlorine. That is done as well. aluminum carbide reacts with liquid water to produce aluminum hydroxide and methane. So we have 7 hydrogens, 4 plus 3, and we have 2. We have 4 aluminum, and we have 1 carbon, and we have 3. So let's just take a stab at the left hand side. Let's just put a 1 there for now. We have aluminum hydroxide and methane. So we can put a 4 for the aluminum and a 3 for the carbon. And let's just see what that gets us. So I have 4 aluminum, that's good. I have 3 carbon, that's good. Now I have 3 times 4 is 12 hydrogens, plus 3 is 4, so I have 24 hydrogens, and I have 3 times 0. 3 times oxygen is 3, times 4 is 12 oxygens. So let's put a 12 in here, and we are balanced. Work your way through. Iron hydroxide plus sulfuric acid gives me iron sulfate plus water. So look at the metals first. So I got 2 here. I'm going to try a 2 and a 1. I have 3 sulfurs. So let's try putting a 3 in here. Well, hopefully our water is going to work out. 2 irons. So that gives me 3, 6. Gives me 18 oxygens. 3 times 1 is 3, times 2 is 6. Plus 12. 4 times 3. That will give me the 18. And hydrogens I have 6. I have 6 in this molecule, and I have 3 times 2 is 6. So I have 12 hydrogens. So when we get to this particular point, we have to remember that there is oxygens present here. So right now I have 12 oxygens in this molecule. So I have 18. I take away the 12 that I need here, which means I need 6. So I need 6 oxygens now and 12 hydrogens. So I'll put a 6 in here and make it work. It's really trial and error as you go through and balance equations. Eventually you'll get there if the equation's correct. Our biggest challenge will be when we are completing our own metathesis reactions. If the ionic formulas aren't correct, you'll arrive at frequently at equations that cannot be balanced. So the word formula weight here in number 3, it says determine the formula weights of each of the following compounds. The word formula weight refers to the actual unit that we see listed. So all we need to do is just list every element that we see, add them up. I have 1 hydrogen, 1 nitrogen, and 3 oxygens. 1 hydrogen is 1.01 U. 1 nitrogen is 14.01 U. And 3 oxygen is 3 times 15.999 U. So we add it up. 1.01 plus 14.01 plus 3 times 15.999 gives me 63.02. AMUs. It's just asking for the formula weights, so we can list it in AMU if we want, or atomic mass units. We know that we're talking about molar mass, where you're just going to convert the U to a grams per mole. Letter B is potassium permanganate, so K, manganese, and 4 oxygens. So 4 times 15.999. You'll get very used to dealing with some of the common elements. Manganese is 54.938. Just looking at our periodic table. And potassium is 39.098. Let's just add them up. 39.098 plus 54.938 plus 4 times 15.999. I have 158.03 atomic mass units. When you're doing these as practice, it's always fine if you just open up a browser and Google what the masses are, and you can kind of check your own work that way. Obviously, it doesn't work like that on tests and quizzes, but it is a good way to practice your work. Calcium, phosphorus, and oxygen. I have 3 calcium, 2 phosphorus, and 8 oxygens. So this is 3 times calcium, which is 40.078. 2 phosphorus, which is 30.974. And 8 times 15.999. Let's check our work here. So 3 times 40.078 plus 2 times 30.974 plus 8 times 15.999 is 310.17. So we do quartz. We have 2 elements, silicon and oxygen. I have 2 oxygen and 1 silicon atom. It's 28.086 U and 2 times 15.999 U. We can check our work. 28.086 plus 2 times 15.999 is 60.08 U. So our next up is gallium sulfide. So we look at our periodic table now that we have names but not formulas. So gallium is found here. It has a charge, if we look up here, as +3. It's in group 13, so most of the elements in that group have a common charge of +3. So I have gallium, Ga, +3. Sulfur's common charge is -2. The ionic formula that we would get out of both of these would be Ga2S3. And now all we have to do is actually just write out the formula like we did above. So 2 gallium atoms and 3 sulfur atoms. Gallium is 69.723 U. 3 sulfur is 3 times 32.065 U. So 139 for the galliums. So 235.64. Chromium 3 sulfate. So the Roman numeral tells us the oxidation state for this is +3. Sulfate is SO4 minus 2. So the formula is Cr2SO4 3 as we cross them over. We get 2 chromiums, 3 sulfurs, and 12 oxygens. Chromium is 51.996. Sulfur again is 32.065. And oxygen is 15.999. A little messy, but I think you guys get the idea. I have 392.18U. And I'm only taking two decimal places, out of each number, because frequently that's what my scale will measure anyway. And taking beyond that is not really that useful. So in question 4, what we're going to do is we're going to be determining the percentage by mass of each element in the formula. So to do that, it's pretty straightforward. You look at what you're being asked to find, so carbon. And in that, what we'll do is we'll then use the total mass of the whole molecule. So I have 2 carbons, so on top I'm going to write 2 times carbon over 2 times carbon plus 2 times hydrogen, and its percentage, so we're going to go times 100%. So when we do that, we can just do the numbers out. So 2 times carbon is essentially 24, we can do molar mass, I guess, grams per mole, over the weight of all of acetylene. So 2 times 12 is 24, plus 2 is 26. So it's the whole thing on the bottom, times 100%. So on, clear, 24 divided by 26 is 92.3%. So the next one that we'll do is hydrogen and ascorbic acid. So percent mass is equal to the number of hydrogens. So 1 plus 7 is 8 times the molar mass of hydrogen, all over the mass of the whole thing. So the mass of the whole thing is pretty easy to do. It's going to be 8 times 1.01 grams per mole plus 6 times 12.01 plus 6 times 16, and we're just doing some rounded numbers here. And this is all multiplied by 100%. So we do our calculation. I have 8 times 1.01 divided by 8.08 plus 6 times 12.01 plus 6 times 16 100 is 4.59% would be the mass of hydrogen. So now we'll look at hydrogen and ammonium sulfate. So percent mass is equal to the number of hydrogens. So 8 times 1.01 gives me 8.08. And then on the bottom we put the mass of the whole molecule. So what we're going to do is we'll just add it up on the screen. So I have 2 nitrogen plus 8 hydrogens plus a sulfur plus 4 oxygens. And I've obviously rounded a little bit. We're just going to get an approximate answer, I guess, here. Over 132.08 grams per mole. So 8.08 divided by my answer times 100 is equal to 6.12% mass. Platinum and PtCl2NH3 So it's the same formula. Doesn't really matter how big it is equal to the mass of platinum. One platinum atom from the periodic table is 195.08 grams per mole all over the whole molecule. It's going to be times 100%. So let's add it up. We can just do it on the calculator again, which makes life a little bit easier. So we add that platinum in, plus 2 chlorine, 35.45, plus, what else do I got in there? 2 nitrogen, so that's 28 grams per mole, plus 6 hydrogen. 300.04 grams per mole. Obviously, if you take more decimal places in from your molar masses, you're going to get a slightly different answer. So 195.08 divided by the answer times 100 is 65.02% mass. So if Avogadro's number of pennies is divided equally among 300 million men, women, and children in the United States, how many dollars would each person receive? So we can just do a little dimensional analysis here. 6.02 times 10 to the 23rd pennies. Times $1 for 100 pennies. So this is Avogadro's number of pennies. It's going to turn it into dollars. So obviously that's 6.02 times 10 to the $21. I wouldn't mind having that. And now I'm just going to take that answer and divide it by 300 million, or 300 times 10 to the 6. I'll resort to my calculator for this one. 6.02 E21 divided by 300 e to the 6. Is equal to 2.01 times 10 to the $13 per person. asks how it compares to the a yearly salary of Sidney Crosby, $8.7 million US. Well, 8.7 million would be 8.7 times 10 to the 6. So it's 10 million times the amount of money is the comparison, and this question is simply looking at giving scale to the size of Avogadro's number. For question 6, it looks for us to actually calculate the amount of various quantities, just using conversions between mass, grams, and moles, particles, and things like that. So it says what is the mass in grams of 0.105 moles of C12H22O11. So I want moles, I want to go to grams. So I need the molar mass of this thing. Let's just add them up on the fly. 12 carbon atoms times 12.01 plus 22 hydrogen atoms times 1.01 each plus 11 times 15.999 times 342.329 grams by 1 mole. 0.105 equals 35.9 grams is the conversion. Moles cancel with moles. We have our dimensional analysis. If I have 143.50 grams of zinc nitrate, how many moles is that? So just apply your conversions. And 1 mole of zinc nitrate is, so let's just add up a zinc atom. A zinc atom is 65.39 plus 2 nitrogens plus 6 oxygens is 189.38 grams. Grams cancel with grams. 143.5 divided by that answer is equal to 0.758 moles. How many molecules is that number of moles of CH3CH2OH? So 1.0 times 10 to the negative 6 moles. We need the formula weight of this, the molar mass of this. So I have two carbons, so I'm just going to do the rounded ones for this. I have 6 hydrogens. And plus 1 oxygen. So you have 46.059 grams for 1 mole. Why did that? Is 4.6 times 10 to the negative 5 grams of something I wasn't asked to actually solve. We're going the other way. So to convert this to molecules, let's just switch to a different color so we can actually answer the question now. 1.0 times 10 to the negative 6 moles times 6.02 times 10 to the 23rd molecules per mole. Probably I could just do this out by power. That's a 10 to the 17 molecules. Here, what's in green is actually what we were asked to solve. And the number of nitrogen atoms in 0.4. 10 moles of NO. So in part D, we have the number of nitrogen atoms in ammonia. We only have one nitrogen atom in ammonia, so it's not really a difficult question. But 0.410 moles of NH3 times 6.02 Avogadro's number. So convert times one nitrogen atom in one molecule. That's 0.41 times 6.02 is equal to 2.47 times 10 to the 3 nitrogen atoms. So I'm going to move that up a bit. Moles cancel with moles, molecules cancel with molecules, leaving me with the unit in the nitrogen atom. So question 7. At least 25 micrograms is what that symbol means of tetrahydrocannabinol, or THC, the active ingredient in marijuana, is required to produce intoxication. The molecular formula of THC is C21H30O2. How many moles of THC does this 25 microgram represent? So we start 25 micrograms THC. 1 gram has 10 to the 6 micrograms, so it's a millionth of a gram. So we're going from micrograms to grams. Now we go to moles. Doesn't matter how big the molecule is, we just gotta do the formula of it. So we'll do just the estimated one. So 21 times 12, so 21 carbons. 30 hydrogens. 2 times is 314.298. So now I'm in moles, so that's actually the first question I was asked. So 25 divided by 1e to the 6. So convert to grams, and then divide by 314.298 is 7.95 times 10 to the negative 8 moles. To go to molecules, we just take that number we just used and multiply it by Avogadro's number. So the answer times 6.02e23 is equal to 4.79 times 10 to the 16 molecules. So that moves us into empirical formulas. The method we solve these is very, very algorithmic. So the first thing I always do is I always assume I have 100 grams of the substance. So that makes life a little bit easier because that means instead of 10.4%, I have 10.4 grams of carbon, 27.8 grams of sulfur, and 61.7 grams of chlorine. So the first thing we're going to do is we are going to turn those to moles. So to turn them into moles, we multiply each by 1 mole over their formula weight, or their molecular mass. So that's carbon, sulfur is 32 grams, so 1 over 32 grams, and chlorine is 1 mole over 35.45 grams. So we do those calculations. It's very systematic. 10.4 divided by 12.01 is 0.865. 27.8 divided by 32 is 0.869 moles of sulfur, and 61.7 divided by 35.45 is 1.74 moles of chlorine. So we're just assuming if we had 100 grams, we're trying to figure out how many moles that would be of each element. So now we look and we find the one that is the smallest, which is the top one, and we divide it all by that. And we get that answer. It's just a law of definite proportions. So one of those 3 elements is present in the lowest possible amount, which is be 1 atom. So 1, this divided by that essentially is 1, and this divided by that is basically 2. 1.74 divided by 0.865 is 2.01. So we're just going to say, I can throw a little approximate symbol on it. So if I were to write this formula, I would have C, S, and Cl involved. I would have 1 carbon, 1 sulfur, and 2 chlorine. That's my empirical formula. So when you do that, the empirical formula may not be what you actually see in real life, but it is the basic ratios of the atoms. This could be any multiple of these quantities. It could be 2 carbons, 2 sulfurs, and 4 chlorines. But the ratio between them would stay the same. So we do the same thing for the other ones as well. So let's try B. 21.7 grams of carbon, 9.6 grams of oxygen, 68.7 grams of fluorine. So each is divided by their ratios. Let's just do them a little bit so that everything kind of fits a little bit better. So carbon is 12 grams, oxygen is 16 grams, and fluorine is 19 grams. The rounded numbers are probably going to be fine enough because at the end we're just going to be looking for approximates. This one is technically approximately 1. So we do that first. So 21.7 divided by 12 is 1.81. 9.6 divided by 16 is 0.6, and 68.7 divided by 19 is 3.62. Find the lowest one, which is that one. Divide by 0.6, divide by 0.6, divide by 0.6, 1.81 divide by 0.6. So just do the math here. 3.01 obviously equal to 1, and 3.6 divided by 0.6 is 6. That one's essentially going to be 3, so we write our formulas out, C, O, and F. We put our ratios in, 3, 1, and 6. And there's our approximate ratios. So for the third one, we do the same thing again. 32.79 grams sodium, 13.02 grams aluminum, 54.19 grams fluorine. So we can get a little bit lazy here and just divide by the molar mass and not really show the dimensional analysis canceling out. Sodium is 23. Aluminum is 27. And fluorine is 19 still. As you work through these, you start coming up with a lot of shortcuts for your work. It's still good to be able to show all the work when you have to. 0.43. 13.02 divided by 27 is 0.48. 54.19 divided by 19 is 2.85. Divide by the lowest one, which is this. So that one's obviously equal to 1. 1.43 divided by 0.48 gives me 2.97. I'm just going to call that 3. And 2.85 divided by 0.48 is 5.93, so we're just going to call that approximately equal to 6. NaAlF, 3 sodium, 1 aluminum, and 6 fluorine would be my empirical formula. So the next question is very, very, very similar, with one additional step. The additional step is that we are trying to determine what the molecular formula is. So the molecular formula is the actual molecule. So what we would find in a solution, or at least when it exists. It's more than just the ratios. It's the actual quantities present in the compound. So it's very similar. We have to determine the empirical formula first. So we're going to do exactly what we did above. So 92.3 grams. Again, we're still always doing that. Assume 100 grams. So 92.3 grams of carbon, 7.7 grams of hydrogen are present, and that's all that's there. So let's divide by their molar masses, 12 grams per mole and 1 gram per mole. Again, I'm using approximate molar masses because it really won't matter at the end. We're going to round at that step anyway. So 92.3 divided by 12 is 7.69. moles, which I guess is approximately equal to 7. But because I wrote that in ignoring significant digits, we're going to divide both by the lower one, which is essentially the same. So this will be equal to 1. 7.7 divided by 7.69 is equal to 1 as well. So the formula is equal to CH and a 1 and a 1. So that is the empirical formula. So now what we do is we find the formula weight for this. So let's just switch to another color here. The formula weight for this molecule would be equal to 1 carbon and 1 hydrogen, or 12 plus 1 equals 13 grams per mole. Now, the formula weight, the molecular weight for this molecule is 104 grams per mole. So to get the ratio, we're going to take 104 grams per mole, and we're going to divide it by the 13 grams per mole of our empirical formula. 104 divided by 13, and it gives me a factor equal to 8. So that factor that's equal to 8 tells me that the actual formula is 8 times heavier than this. So I'm actually going to multiply this empirical formula by 8. So instead of C1, it'll be C1 times 8, so C8 and H8. And that would be the molecular formula for the molecule. So the ratio is the same. There's equal numbers of carbon and hydrogen, but one of them is the actual molecule that we would expect to see. Caffeine contains 49.5 grams carbon, 5.15 grams hydrogen, 28.9 grams nitrogen, and 16.5 grams of oxygen. This is a great time if you haven't done any of these or you weren't really sure to give it a pause and try and solve this one and the next one and see how you make out. I'm going to divide each by their molar mass. So 12 grams per mole, 1 gram per mole, 14 grams per mole, 16 grams per mole. So we will actually do out our calculations where we can. The hydrogen one's pretty easy. 49.5 divided by 12 is 4.13. 28.9 divided by 14 is 2.06 moles, and 16.5 divided by 16 is 1.03 moles. Look at the same deal. That's our smallest. So 413 divided by 1.03 is equal to 4. These are pretty predictable, really. Exactly equal to 5. And this is going to be equal to 2. So there's our ratio. So I have CHNO, C4H5N2, and 1 oxygen. So we get our formula weight. Won't write it out this time. We'll use the calculator. So 4 times 12 plus 5 hydrogen plus 2 nitrogen plus 1 oxygen. The formula weight is equal to 97 grams per mole. The molar mass is 199.5. So you can actually write it out if you want to or you have to. Divide it by 97. 199.5. I just want to make sure that it's the right, exactly what the quantity is equal to 2.06 in the difference. So we're going to double everything in here. C8, H10, N4, O2 would be the mass of caffeine. So the mass, the formula of caffeine. We'll move to our last one here. MSG, some people are familiar with. It is the same process that we just did. 35.51 grams of carbon, 4.77 grams of hydrogen, 37.85 grams of oxygen, 8.29 grams of nitrogen, and 13.60 grams of sodium. So we're just going to go through this exact calculation again, just more compounds. It doesn't really change anything. This time I'm just not going to even write my units. I'll just tell you what I'm doing. We'll just do it nice and quick because we're going to need a little bit more room. So divide it by 12 grams per mole, 1 gram per mole, 16, 14, and sodium is 23. So we're just going to convert to moles. And these are all in grams per mole. Just to put the unit there at the bottom. Satisfy any of those sticklers. 35.51 divided by 12 is 2.96. 4.77. 37.85 divided by 16 is 2.37. 8.29 divided by 14 is 0.592. 13.6 divided by 23 is 0.591. So we have our smallest, 591. So we're just going to divide each of these numbers by 0.591. Just do it right down the list, I guess. So those two bottom ones are pretty much 1. 2.37 divided by 0.591 is 4. 4.77 divided by 0.591 is equal to 8. And 2.96 divided by 0.591 is equal to 5. So we have our formula. Write them out in order. Empirical formulas, it doesn't really matter. So C5, H8, O4, N1, sodium 1 would be the formula. So we know the molar mass is 169, so let's check our formula weight. So again, as we're just kind of breezing through these, let's just use the approximate one and compare it. So 5 times 12 plus 8 plus 4 times 16 plus 14 plus 23 is 169 grams per mole. That is the actual molar mass. So that means the molecular formula is the same as the empirical formula. And there it is. As we kind of go through. Now, on our final page, what we have going on is we have just a couple limiting reactant questions or limiting reactant stoichiometry questions. So we're just going to have a. So as we look at this question, we have the fermentation of glucose, C6H12O6, produces ethyl alcohol and carbon dioxide, and the formula is listed there. So how many moles of CO2 are produced when 0.400 moles of glucose reacts in the above fashion? So let's assume that that is my limiting reactant. Because it doesn't tell me any other information, so I'm going to have to make that assumption. C6H12O6. Alright, so I'm already in moles of this. We never work in grams, so we're already in moles, so we just need to convert that to moles of CO2. So 2 moles of CO2 for every 1 mole of C6H12O6. So basically I'm just going to double this. So we should see 0.8 moles produced. How many grams of glucose are required to form this amount of ethanol? So we're in grams, so we got to go to moles. We just do not work in grams pretty much ever. So let's go to 1 mole, C2H5OH. Need the formula weight of ethanol. So 2 times 12.01. There's my carbons. 5 hydrogens. Oh, forgot one. It's 46.08. So I've gone from grams of ethanol to moles of ethanol, and now I need to go to apply my ratio. 1 mole of glucose, C6H12O6. So for every 1 mole that I got, so I'm going to put that on the top of my fraction. I need to cancel out the ethanol, so that's 2 moles of C2H5OH. So now I am in moles of glucose, and finally I need to convert that to back to grams, so we need the molar mass of glucose. So let's add them up. 6 times 12.01 plus 12.12 plus 6 times 15.999 is 180.17. And this is glucose. I'm just going to GL for glucose. So I really run out of room. Check my dimensional analysis. Grams of ethanol, moles of ethanol, moles of ethanol, moles of glucose to moles of glucose, leaving me with grams of glucose, which is what I was asked for. So we can roll through this. So 7.5 grams is my starting material. Sort of, I guess, my product that I want of ethanol. Turn it to moles. So that many moles. My next step is to convert the using the mole ratio, so divide by 2. There's my new number. And then I multiply it by the molar mass to go back to grams. So I would need 14.7 grams of C6H12O6 to make that work. Now, depending on how you actually record your values along the way, the next question can probably be a lot easier. We're just going to go through the same steps again. So 7.50 grams of ethyl alcohol, C2H5OH. So once again, grams of ethyl alcohol, gotta go to moles, or ethanol, I guess. 46.08 grams. So I am in moles. I get 2 moles of carbon dioxide for every 2 moles of ethanol. And now I just need mass of carbon dioxide, which is 12.01 plus 32, 44.01 grams. CO2 per 1 mole CO2. We've all sort of done out here. Grams cancel with grams, moles cancel with moles, moles cancel with moles, and that's going to give me my final answer. So 7.5. We'll work our way through. 7.5 divided by 46.08 times 2 over 2, which is basically nothing. 44.01 is my mole, equals 7.16 grams of CO2. And that brings us to our final question on this handout, which looks at more dimensional analysis style questions. So it says a piece of aluminum foil, 1 centimeter by 1 centimeter by 0.00055 centimeters is allowed to react with bromine to form aluminum bromide. So we got to balance this thing. I have a 2 and a 3, so I'm going to use the lowest common multiple. And there we go, we're balanced. 2, 3, and 2. I have 2 aluminum, 6 bromine, 6 bromine. So it's telling me what density is, so we know that density is equal to mass over volume. So the first step I'm going to do is find the volume. So volume is equal to the product of the 3 sides, so 1 centimeter by 1 centimeter by 0.0005550 centimeters equals 0.0005550 centimeters now cubed. So I got the volume. Step 2, find mass. So if density is equal to mass over volume, mass is equal to density times volume. So we'll use that relationship. Mass is equal to density times volume. The density is 2.699 grams per cubic centimeter times 0.0005550 centimeters cubed. Centimeters cubed is going to cancel. 2.699 times 0.00055 equals 0.001484445 grams of aluminum. And step 3, is convert to moles. So 0.001484445 grams of aluminum. 1 mole of aluminum is 26.982. Equals 5.50 times 10 to the negative 5 moles of aluminum. So 0.5 millionths of a mole is present. So C says how many grams of aluminum bromide form, assuming the aluminum reacts completely. So start with our starting material. As many moles of aluminum. Look at our ratio. So it wants aluminum bromide, so it's 2 moles of aluminum bromide. We put that value on the top because that's what we want. For every 2 moles of aluminum. Now I need the formula weight of aluminum bromine for the top here because I want to go to grams. So aluminum is 26.982 plus 3 times bromine, which is 79.904, is 266.694 grams of aluminum bromine for 1 mole. So moles cancel with moles, moles cancel with moles, leaving me with grams. So 5.50 exponent to the negative 5 moles times 2 over 2, 266.694 equals 0.015 grams of aluminum bromide. And there's our answer.